hey, what's going on here? Complex numbers in polar form. Polar form? Well, I Google search polar and look at what I came up with. Aren't they cute? Look at this here. Oh, beautiful. Oh, lovely pictures of polar bears. And this is a big fella. And hey, I don't like the look on this one's face. I think we'd better get off this page and see what polar form for complex numbers is. Here we go. Polar form is a coordinate form which is different from Cartesian form, where you specify a point P by a radius and an angle. Okay, so we call this the pole. Here, the point of the origin, 0, wherever we're measuring from. And we talk about how much we turn and how far away we are. I think, in a sense, polar form is more what we use in everyday life with bearings and stuff. Turn this angle from true north and go this distance, rather than a latitude and longitude like an XY system. Okay, so we're going to have a look at the polar form way of describing a complex number. So let's have a look a little bit more at that. So here we'll come down here. We have the usual set of axes here, x and y. We should actually have those labelled. And the polar way of describing this point down here would be to say, well, what angle has it turned through? Okay, so we were given a hint here, pi on 4 to there. But with polar form, the convention is to specify the angle between neg pi and pi. So here we want to know this angle. And what would it be? It'd be neg 3 pi on 4. And we want to know this distance. Well, I'll tell you what that is. It's 2 actually here. So this point P would be specified by 2 and neg 3 pi on 4. That's the method of polar coordinates, and not seen those before. Okay, so we're moving away from the Cartesian system there a little bit with right-angled axes. But on the Argand diagram, we can have sort of both systems operating. Okay, so that's what we're going to investigate now. Let's express points on the Argand diagram in both forms now. Okay, so let's have a look at what it would look like. Here we go, the real and imaginary axis. So here we would specify point P by these 2 coordinates. Okay, and we could specify this vector by x plus yi. Okay, that's what we've been doing. That point P can be reached from the vector x plus yi. Okay, complex number. Very nice. Now, let's try to work with point P not being xy, but r theta. What would r be and what would theta be? How could we work them out? Okay, so come on down and let's do some. And here's some clippings from Hayes and Harris publications here. And I think you can see that if you looked there at this point, and that was r, this is r cos theta, r sin theta, using what's cos theta here. The x coordinate is the adjacent to the angle theta. So x is, we'll put it this way, x over r is the cos of theta, adjacent over hypotenuse, so x equals r cos, oops, put the s first, cos theta, and here the y coordinate is the opposite, so it's opposite over hypotenuse is the sine of theta. So we can connect this old system of x and y values, or real and imaginary values, to our polar system. So here, what could we say? Well, this, here we are here, but I'd like to unpack this a bit. X plus yi, or iy, is what? X is r cos theta, and y is r sine theta. So therefore, our complex number with these polar sort of approaches, r and theta, it looks like that. Now, we could take r out as a common factor and say that the complex number is z equals r times this little bundle. And because it's going to be the same for every complex number, it's going to have a cos theta and an I sine theta, we replace that by cis theta. Okay, and also r is the length of that vector representing our complex number, so it's mod z, cis theta. Interesting, neat little package, isn't it? It's nice and neat, as long as you remember what's going on there. So this is the distance, this is the r, and this theta is the angle that that vector makes with positive direction of the real axis. So in here, in other words. So we've got to remember that we use the theta from neg pi to pi. Okay, what that means is if you're in these quadrants here, it's going to be negative. These quadrants here, it's going to be positive. We've done that before with basic trigonometry. All right, what do you think? Want to try and do some? Let's see if we can do this conversion. So just summarising that now, and you might write this down. Any complex number z with that Cartesian form can be converted to this polar form, where the size or the radius is the size of the complex number z, and theta is called the argument. So that's the modulus, we know that. The argument of z, okay? So that's the angle that it makes. And it is that sort of little rule, because we know the point P at the end of z here is r cos theta, r sine theta, using the polar values, polar coordinates r and theta. Okay, and then we are going to abbreviate cos theta plus I sine theta as cis theta. Oh, is your head spinning yet? Now we've got another way of looking at a complex number, and we've got to be able to use either forms quite clearly. All right, come down now and let's have a look. Here's an example. Let's have a look at 1 plus I. So if we plot it, it'll be 1, 1 out there, our complex number. And here, what will that length be by Pythagoras, or the length, the modulus of the complex number, square root of 1 squared plus 1 squared, to be root 2. And the angle, quite clearly, here will be pi and 4, because the tan of theta, let's just use tan in there, is 1 over 1. So theta is the angle whose tangent is 1, which is pi and 4. Okay. Now when you're doing this conversions, a diagram is very important. You can't just use the tangent, because you might have that ratio over here somewhere, 1 and 1. And that's a different angle. So you have to work it out, similar to what we were doing with circular functions before. You need a diagram to adjust the angle. We'll come to that later. So therefore, what have we just done over here? 1 plus I is r, cis, theta is pi and 4. So that's the polar form of 1 plus I. Got to be able to flick between both of them. So coming up, I ask, why would we do it? You might be asking that already, so you have to wait now and just see why we are asking to be flexible here. 2i, let's plot it, always good. 2i is 2 units up the imaginary axis. So the size of it is the length of that is 2, and the angle is pi on 2. So 2i is 2 cis pi on 2. What about neg 3? Neg 3 is on the real axis here, its length is 3. The angle is clearly pi, so neg 3 is 3 cis pi. So you can do everything, any position on the Argand diagram now. 1 take I down here, so there's the angle, isn't it? This is 1 and 1 here, and so the length of this is going to be root 2, or square root of 1 plus 1. And here the angle is clearly down in the 4th quadrant, which we have the convention, remember. We're going to go from neg pi to pi, and therefore it's neg pi and 4. So 1 take I is root 2 cis neg pi and 4. Okay, getting the hang of it. Let's do it on the calculator now. Can you do that? Here's the Casio, and it's in run mode, and I've hit options here, in there, hit options, and got this window. Okay, you see what we want. We want complex, so we'll hit F3 down below there. Okay, and this is the window we get up for complex now. And you can see we can do a lot here. We can find the absolute value, we've done that before. We can find the angle, the argument. So both of those, if we hit abs and did absolute value of a complex number, probably wouldn't bother. It's easier just to work it out by hand, isn't it? Or the argument. So we could go arg in brackets 1 plus I, and that would give us our argument there, which was one we did before, pi and 4. So the calculator can do it for you. I encourage you though to do it by hand so that you can really see what's going on. We are in this course very interested in the geometry on the argand plane. Okay, come down now, and here's a chance for you to do some work. I would probably do them by hand with diagrams to just check everything out, and then also by the calculator, okay? Drawing a diagram is important if you're going to use tan neg 1 of the opposite over adjacent to work out the angle or the argument. So theta is that, but you've got to check the quadrant. Okay, check the quadrant. All right, so diagram is important. Okay, have a go, and I'll show you the solutions now. Okay, so there's question 1. Just check them out, little diagrams there are important. Okay, come down. Question 2 and 3. Just check question 3. It might be worth going through that with fellow students, make sure you understand that, or your teacher. All right, let's move on. And here it is, the answer that you've been, well, a question that you've been wanting to get answered, I guess, is why do it? Hey, Huddy, this is really confusing my mind. I was happy with x plus yi, and now you brought this in. Well, would you be happy with x plus yi if I asked you to do this? Ooh, binomial expansion. Lots of work there. Hey, this is worse. Hey, we're multiplying lots of complex numbers together. And what about dividing? That was never friendly. We had to do this, didn't we? Now, something fantastic, absolutely fantastic, is going to happen now. The answer to why do it is that the r cis theta form, z equals r cis theta, is just beautiful to use in multiplication and division of complex numbers. It's absolutely fantastic. So that excitement's coming up. Let's go and have a look. Okay, here it is. Multiplying and dividing in polar form. Multiplying, okay. Now, they haven't put the r's in here. You know, you could have r1 and r2. So let's look at what it involves. Let's leave the r's out for the moment. Just cis theta, that's cos theta plus I sine theta. Now the other complex number's got a different angle. So this is the way we would generalise a proof in polar form, not a plus bi and c plus di. We would simply have different angles here. That covers it. And let's leave the r's out for the moment. So when you do this, expanding it all, they've collected all the terms up. Okay, so we've got cos theta by cos phi, and then I sine theta by I sine phi is I squared sine theta sine phi, so that's minus in there. So they haven't done the full expansion, they've just collected the terms as we go. So if you look at this term, it's the ones with i's, so it's that one, I by sine theta cos phi, and I by cos theta sine phi. So how many i's have you got? It's this big term here, that's the imaginary part of the complex number. Okay, and this is the beauty. Watch this, watch this. Do you recognise that pattern? Cos cos minus sine sine. That is the cos of the two angles added. Sine cos plus cos sine, that's the sine of the two angles added. Do you remember those formulae? Go back and check them. They're called the addition formulae for circular functions. Okay. So something absolutely beautiful has just been proven, and that is if you multiply two complex numbers, the resulting complex number has the sum of the arguments. So multiplication, multiply, implies add the arguments, the angles. So it's very, very nice. Okay, so with a 1 plus I squared, you don't have to expand it. You're going to call this root 2 cis pi on 4 times root 2 cis pi on 4, which is going to be root 2 by root 2. Multiplying the moduli, that's still straight, isn't it? There's no problem with that. Okay, and then it's going to be cis, what we've just proven up above, pi on 2. Okay, adding the arguments. That's what we've just proven. You can add the arguments. How neat is that? Rather than expanding binomially 1 plus I squared. And of course, the more product, the longer the product is, the easier it becomes. So can you just notice, come back up here with the R1 and the R2, quite clearly we're just looking at the cis part, because it is understood here that the product of those two moduli would just be R1, R2, they're real numbers. Okay, so you're just going to multiply them together out the front. We're going to come back and look at that. But we wanted really to look at the beauty of this. Multiplying complex numbers in polar form, you add the arguments. Oh, we better look at the geometry of that. That's going to be interesting. Okay, come down and let's look at division. So cis theta divided by cis phi, two different complex numbers now. You might think of this as Z1 and Z2 in general polar form with different angles. So if we do a little tricky-do here, multiply top and bottom by cis neg phi, the bottom one, this is equivalent to, compare with multiplying by x take yi, the conjugate, isn't it? I wonder if you can see geometrically whether that is equivalent to the conjugate. We'll have a look at that. Neg phi, would that be the conjugate of, or cis neg phi, would that be the conjugate of cis phi? Do you think? Let's have a look. Cis phi, it's real and imaginary. Cis phi, if phi was here, that'd be Z2 we called that. Then neg phi, oh yeah, would be down here, reflection in the real axis. That should be the conjugate, shouldn't it? Oh, so we're doing a similar thing here. Let's look at the top. We're multiplying these complex numbers together, so we add the arguments, so theta plus neg phi, over cis of naught. A cis of naught, we better look at that. That's cos naught plus I sine naught. Cos of naught is what? Cos of naught is 1. Sine of naught is naught. So the answer is 1. So this is dividing by 1. Hey, we've just got another nice result. I'll put that there. It's just naught equals 1. We've just proven it down here. But what do we see here? Dividing two complex numbers, what do? You subtract the arguments. Oh, that's nice. You don't have to do the multiplication by the conjugate. So if you had something like this, what can we do? 1 plus I over, what's another one that we did before? Something like, what is it? What's a good one? Root 3 over 2 plus a half I, something like that. So hang on, we'll just get rid of that. And so if we change it to polar form, it would be root 2 cis pi on 4. And this one here, what length has it got? Let's have a look. 3/4 of a quarter. This is 1 cis. Now, this is the cos, and this is the sine, so you might recognise the angle, so it's pi on 6. Now let's do, the division of this is just normal real number division, so it's root 2, but now it's cis pi on 4 take pi on 6. A little bit neater, so we could work this out in terms of pi and whatever that is, so it's root 2 cis, call pi on 4 what? 3 pi on 12, and pi on 6, 2 pi on 12. So this would be pi on 12. Oh, so that's a bit easier than multiplying top and bottom by the conjugate, isn't it? If we had this thing here, that would be quite nasty. To do a division, we'd have to multiply by the conjugate of this thing. So this is nice. Okay. So are you getting the hang of it? You can see now, perhaps, if we want to multiply or divide complex numbers, the polar form is the go. Okay. Come down and let's look at the last little property of cis. Okay, so cis of theta plus k 2 pi. Okay, using those rules from above, it's the same as cis of theta times cis of k 2 pi. And that's times 1, which would be cis of theta. Now, that's doing it with algebra. Can you see why that would be the same? Let's do it on the diagram. So if you went here to theta and went around 2 pi, you'd be back to the same point. So this is the property of circular functions again, isn't it? If you go around 2 pi, you return to the same point that you had in the beginning. So that's a geometric way of explaining this. We've done it with the properties of the argument here. That if you add over here k times 2 pi to the argument, then you've gotten this line, and cis of k times 2 pi is just 1. Cos 2 pi is 1 and sine 2 pi is 0. Okay, so how do you reckon that's going? That's an interesting one as well. Alright, so let's get into some of the geometry now. We've got to keep our eye on the geometry of this because it's quite handy looking at the Argand diagram to see these relationships. So I guess you can see here that when you do this, adding k times 2 pi, that's equivalent to a rotation of 2 pi. When you add the argument, that's going to go around 2 pi more, thinking about that geometry. All right, let's have a look then at what we've got. A summary, you might like to write these down. So if you're multiplying two cis forms together, we're leaving out the r now, the modulus, you will add their arguments. So multiplying is adding the arguments, and dividing here of two complex numbers is subtracting the arguments, one in the numerator minus one in the denominator, get rid of that. And down here, the idea, if you're going around an integral number of 2 pi's, I didn't mention that before, that is important, an integral number of 2 pi's, you're going to be back to the same point on the Argand diagram, so they are equal. All right, let's have a look at doing some. So here we are, use properties of cis to simplify, cis pi on 5 times cis 3 pi on 10. Come over here, write them out, and then multiplication of cis form, you add the arguments. Pi on 5 plus 3 pi on 10, converting pi on 5, multiplying top and bottom by 2 to 2 pi on 10. Now that's an important trick. If you've got different denominators, you want a common denominator. So it's 2 pi on 10 plus 3 pi on 10 is 5 pi on 10, which is cis pi on 2, and we can change that back to x plus yi form if we wanted to. Okay, what about this one over here? Here it is, cis pi on 5 divided by cis 7 pi on 10. Division, as we've proven above, is the subtraction of the arguments, so we want to change this again. This is 2 pi on 10 minus 7 pi on 10 is neg 5 pi on 10, or neg pi on 2. And then if we do cos plus I sine, the cos of neg pi on 2 is 0, the sine of neg pi on 2 is neg 1, so we've got neg I. Okay, interesting, isn't it? Keep your mind clear on this, just be able to flick from one form to the other. And really, it's important to look at diagrams and see what's happening there. Okay, well, come down now and let's have a look at this 2D2 question 1. We've got a few problems here. All right, so I want you to go through every one of these. It's very, very important because you're going to get the hang of both the conversion or the form represented by cis, and also the geometry. So you might try to plot the answer in cis form at the end. All right, let's have a look at some answers for these. Okay, so there's the first few. Can't get them all on the page now. And now the last few. Okay, have a look here, this multiplication to the fourth, isn't that nice? Okay, a lot easier than the binomial expansion of x plus y I form. All right, let's move on. Here's a couple more problems, okay, using the properties. I think this question here, number 3, is very important in getting your head around the geometry on the Argand plane. And they do love in this course the geometric interpretation of what we're doing. All right, pause it and have a go. Let's look at the answers. 2 and 3. All right, moving on, let's do a bit more now and have a look. Here's another example. So write this one in polar form and multiply it by 2 cis pi on 6. Okay, so let's first of all plot it. Remember what I said? 1 and here root 3, 1 plus root 3i is represented by that vector. Okay, now the size of it over here is real part, square root of real part squared plus imaginary part squared. Okay, that's all right. So here we would then say 2 outside of this. Now the way Hayes and Harris have done it here is dividing that through by 2. You've got cos theta and I sine theta. So you want an angle whose cos and sines are those, or if you've got a diagram, tan neg 1 of what? Okay, so it's a tangent would be the opposite here, or the y value over the x value. So it's tan neg 1 of root 3 over 1. Or you can just pick it from here. What angle do you know has a sine of root 3 on 2 and a cos of a half? So it's pi on 3. So you're going to identify that way. Okay, so you can do it that way, or you can pop it onto the calculator. So you've got 2 cis pi on 3. So whatever way, this is dangerous here unless you've drawn a diagram to see it's in that first quadrant, because you might get the same tan value down in the third quadrant where tan again is positive. Okay, so just check that. You can use either way here. All right, the idea of identifying that as cos and that as sine, or simply tan neg 1 of the y over the x in the x plus y form, x plus yi form. Okay, so now let's multiply by 2 cis pi on 6. So we've got that and that. We've just changed the first one to 2 cis. This one's in cis form. So we multiply the moduli together here, the r values, just real numbers, and then we add the arguments. So sometimes to remember this, I go, ma, sounds like a sheep, doesn't it? Multiply, moduli, add arguments. Okay, so you could do that mark like that. Okay, to remember that rule. And pi on 3 plus pi on 6. Well, pi on 3 is 2 pi on 6, isn't it? Multiplying top and bottom by 2. So that's now 3 pi on 6, or they've gone straight to pi on 2. And if you do x plus yi form, cos pi on 2 plus I sine pi on 2 is that, so it's 4i. All right, try and keep your head around this and just go forward carefully. And now they ask us what happens, what's happened there. Well, we started with this complex number, and if we multiply by 2 cis pi on 6, what happened? Well, we multiplied the modulus by 2, so it's gone out to twice the distance. This had a size of this one was 2. And now it's gone double in length, so we're very interested in the geometry here. And it was what's happened, we've added the arguments, haven't we? So it's rotated, look at this, the geometry, it's rotated through that extra angle there. So it's actually hit the imaginary axis. Now that's important to see what's going on. If you're going to come up here, if you're going to add the arguments, it means you're going to rotate the complex number around, aren't you? You're going to add its argument, and there we're going to rotate it anti-clockwise. That's the way we move on the in the circular functions method. Anti-clockwise is positive. Okay, so just make this note down here. Multiplying by r cis theta in general dilates the original complex numbers vector by a factor of r, so it's going to be r times the length, and rotates it through an angle of theta. That is a bit of geometry, and the way this course has gone, it's very important to understand the geometry of the Argand plane. Okay, let's go down and you can have a go. So here's 4 and 5. Pause the presentation and see how you go. I'm going to show you the answers now. Okay, be aware of any geometric statement. It's very, very important that you see it, see what's going on. Just don't do the mechanics. Okay, let's move on. A little bit more to do. We're getting there. Here's another example. Use complex number methods to write cos 7 pi and 12 and sine 7 pi and 12. This is really just an algebraic oddity. It's not going to be asked in exams. It's just an interesting point. So if you made up the complex number cos 7 pi and 12 plus I sine 7 pi and 12, you could say that's cis, that's our abbreviation for cos theta plus I sine theta. We abbreviate as cis, combination of cos and sine, cis theta. Okay, so we're going to write that, and then we could break it to understand these better into 3 pi on 12 and 4 pi on 12, and the reason for that, of course, these are common angles. So this original cis 7 pi on 12 could be thought of as the product of cis pi on 4 and cis pi on 3, and then we can change it back to x plus y I form. Okay, and if we do that and expand this, we get this and this. So cos of 7 pi and 12, our original one, back up here, is the first part, the real part. Sine 7 pi and 12 is the imaginary part. Okay, so here we're equating real and imaginary parts there, and we've got these answers. So it's interesting, isn't it? We've gone in a sort of circle there, gone into cis form for the ease of this thing here of multiplication, and then or splitting, sorry, and then calling it multiplication, and then putting the values of common angles in. So the shift here was to use common angles that we know the sine and cosine for, these two here. Okay, so it's an interesting little trick you do, that one. And what's been happening, this is our picture over here. Okay, so that cis pi on 3 and cis pi on 4 made up our original sum. Okay, so when we do that, we got these points on the Argand plane. That was the idea. If we can bring in pi on 4, we've got its common values. If we can bring in pi on 3, we've got its common values, and that's how we can eventually come to a surd form, or in a simple surd form for the two individual ones. All right, so looking at the diagram and just thinking about what's happening with this cis form is important. Okay, do you want to try some? And this is not a bad idea. I wouldn't spend too much time on this. The idea is, of course, to convert to common angles whose surd values for sine and cosine are known. Okay. All right, let's have a look at the answers to those. Okay, so there we have part A, and our conclusion at the end. Once we've got real and imaginary part, then the cos is the real part and the sine is the imaginary part of our complex number method, cos theta plus I sine theta. Let's have a look at the part B now. Yep, and so we're doing the same thing, bringing in common angles here. That's the idea. going from there to there, using common angles, and then breaking it down and putting in the values that we know for the cos and the sine of pi on 4 and 2 pi on 3. Alright, and then equating real and imaginary parts again. Alright, let's move on. We're nearly there. I hope you haven't got too much of a headache at this stage. Alright, so let's just summarise the properties of argument now. If you have two complex numbers multiplied together, you add the arguments. That's the MAR thing. Multiply moduli, add arguments. If you're dividing two complex numbers, the overall argument at the end is the difference of the arguments. If you're finding the argument of a complex number raised to a power, then it's n times the argument of a complex number. I think you could see that if you're doing this n times, then you're going to have a cis form for each one. Okay, cis theta, that's the argument. And what do you do when you multiply complex numbers? You add all the arguments, but they're all the same. There are n lots of them, so it's n times theta, or n times the argument of the original z, that idea. Alright, so we can use those to simplify expressions. Let's look at an example now. Use polar form to establish this result that we've done before with a plus bi and c plus di, if you remember. And also that the argument of a product is the sum of the arguments. Okay, so in proving now we need a general form, a general polar form for the two complex numbers. So z is size of z cis theta, w or omega is the size of w cis phi. Okay, that's the way we generalise it. Confer with or compare with a plus bi and c plus di in Cartesian form. Okay, back with that sort of form. Okay, let's have a look at the product of the two. There we have it. What do? You multiply the two moduli together, add the arguments. And if you look at it, now what's the size of this? It's the number out the front, it's r, isn't it? So the size of that is size of z by size of w, and we don't worry about this. This is the angle. Just let's recap on that. This is the real and imaginary axes. So if we're doing this for our complex number, let's just take z. Theta does not affect the size. Here it is. That's the size or the modulus of the complex number. Okay. So when you multiply the two numbers together, you are clearly here out the front multiplying the two r's together, so you do get the result you want. Okay, and what can we conclude? The argument of the product of these two is the sum of the arguments. There it is up there. Okay, so argz plus argw. Okay, so we can see it from that sort of little proof with our general form. Just remember that now. If you're looking at proving it in polar form, you're going to use a modulus out the front for the size, and theta and phi, or alpha and beta or something. It's customary to use theta and phi in our proof set. Alright, come down and see another little bit of work here, and you're nearly finished. Okay, root 2 cis theta, find the modulus and argument of 2z. Okay, so let's double it. It's 2 root 2 cis theta. So what is the size of that? It's the r value out the front from what I've just said with that geometry. And what's the argument? It doesn't change by multiplying by that real number. It only changes the length. Think about that geometrically. Okay, what about iz? I is cis pi on 2. Why do we do that? Because z is in polar form. So if we're going to multiply by another complex number, change it to polar form. Not a bad little rule there. You wouldn't generally multiply x plus yi or Cartesian form by r cis theta form. Convert them to the same form, and in multiplication it's the cis form, so I becomes cis pi on 2. And root 2 is out the front. This size of this one is 1. and then you add the arguments. So finding the modulus and argument, we've got root 2, and the argument is theta plus pi on 2. So that's actually looking at, we've done this before, looking at that on the plane. If that was theta for z, what's happened, it's gone rotated 90. Okay, it's rotated around 90. And so the size, this had a size of root 2. The size won't change, but the angle will, okay, around there, and that's a rotation. So keep that in mind. You're adding pi on 2, that's turning it around there. All right, let's have a look at part C, 1 take I times z. Okay, so 1 take I has to be converted to root 2 cis neg pi on 4. Let's do it over here. 1 take I, so looking at that, that's going to be a tan of 1, and the argument therefore, the angle, is neg pi on 4, remember down in that quadrant, because we follow this convention from neg pi to pi. Okay, so now we can multiply 1 take I by z, that's root 2 cis neg pi on 4 by root 2 cis theta, and we'll multiply the moduli, so that becomes 2, and cis of neg pi on 4 plus theta. Okay, so what is the argument? What is the size of this complex number? The modulus is 2, and the argument is that. So that's neg pi on 4 rotation now, so it's gone down under the axis there, or not under the axis, you're adding on neg pi on 4. So what would that look like? If that's theta, you're coming down pi on 4. Okay, with no change in the, this one has got a change. So this has become, root 2 has gone to 2, because the size of the other complex number was not 1, it was root 2. So think about that geometry. All right, come down and have a go. There's a couple of little things to play with there of a proof nature. Okay, have a go and I'll show you the answers now. Okay, 2d3, and this is some little proofs there. Notice instead of R1 and R2, they've let big R and little r, okay, to generalise that. Okay, so you can use that. Let's have a look at the rest of question 2. Okay. Study that. You're building up a few skills. I hope you're getting your head around this. You might have to go back and check it out again. All right, last little bit, come down and we'll just finish off with a couple more examples here. So here we're looking at Z in cis form, cis thigh, where thigh is acute. Determine the modulus and argument of Z plus 1. All right, so here's Z, let's plot it, and plus 1, so we're looking at the modulus and argument of that. Okay, so if the size of Z is 1, it lies on the unit circle, and Z plus 1 is OB, if you like, out there. Now, what can we do? Let's look at the geometry. So the first thing you notice is you could make a parallelogram there, which actually would be a rhombus, because we've said cis thigh, the size of that Z there would be 1. Okay, so not only is it a parallelogram from what we've discussed before, if you put 1 there and you're adding 1 and close that off, the Z plus 1 is a diagonal of the parallelogram, always there. And now it's a rhombus because we've got equal sides, because we've added 1, and that's the size of our original complex number up here. Well, there's no number in front, which means its modulus is 1. That makes it a rhombus. And then we can say, what is the argument here in there of Z plus 1? The argument of it will be a half the angle that Z had, so this was theta in here, because the diagonals of the rhombus bisect each other, and also bisect the angles, okay, in the corners there, at the vertices. Okay, so therefore we've got our argument, and then we can also say for our length now, what's our length? If we have looking at the cosine of theta on 2. Let's have a look. Diagonals of a rhombus bisect each other. Got to use that. We've got theta on 2 here. So the cos of that is OM, which is that length there, is OM over 1, right? Adjacent over hypotenuse. So what that means is OM is the cos of theta on 2, and what is Z plus 1? Remember that diagonal is bisected down to OM, so the length of Z plus 1 there is 2 times the length of OM. So it's 2 cos theta on 2. So the size of Z plus 1 is 2 cos theta on 2. Now that's a little bit tricky, isn't it? Again, it's coming back to the idea that when you add vectors up, you can create this parallelogram, which in this case becomes a rhombus because of the numbers there that we're using. All right, get your head around that. That's getting a little bit harder. Okay, so here's some little problems for you. A little bit of geometry here. So just remember things like the triangle inequality and just relating the complex numbers to the diagram. You must relate them to the diagram and see what's going on there. Okay, a bit of geometry for you. Okay, let's have a look at the answers to those now. So here is question 3, first bit of it. Let's just go down. A lot of geometry happening there. We'll go through that with your teacher. And there's the rest of it. A bit of cosine rule in here. So we're trying to bring in a lot of stuff. Remember, maths learning is sequential and cumulative. And therefore, you must build up your toolkit and remember it. Accumulate skills. Let's have a look at 4 now. Okay. Look at that diagram, make sure you've plotted those correctly. And think about the geometry of division. Okay, subtracting arguments. And then that one. Okay, some little tricky do's there. Study it carefully. All right, let's finish off. Okay, and let's do conversion between Cartesian and polar forms, because as I said, if you're going to multiply, you've got to have them in the same form. So x plus yi is Cartesian, r cis theta is polar form, and the relationship is the size, or the r value out the front, is the modulus, which is the root of real part squared plus imaginary part squared, and the angle is y on x, or the cos and sine of the angle of the argument are those values. Cos is the x over the root over the modulus root x squared plus y squared, and sine is the y value. Okay, so all of those results come from this diagram, because the y is the opposite and the x is the adjacent. So that's related to cosine and sine in those two ways. All right, just checking that. Let's go and have a look and do some on the calculator. Polar to Cartesian, 2 cis pi on 8. You'll do cos pi on 8 plus I sine pi on 8. Make sure your calculator's in radians before you look in there. So on the Casio, go shift menu to set up and scroll down to the angle. So check your calculator for radians there. Okay, and over here, we've seen that window again. This is from the TI, but we've got the ones we want here also in those positions on the Casio. You don't need those here because you know the modulus and argument, but you do need the I. So you put 2 cos pi divided by 8 plus I sine, and it will give it to you like that. Or you can just do it in run mode there. You don't need the I there perhaps. Be flexible, be able to do it on your calculator. So then Cartesian to polar, there you are. So here, what is the first thing? Find the modulus, which is the square root of real part squared, imaginary part squared. The length here is root 10. Draw a picture of where it is. Neg 3 plus I is out in that quadrant. So there's your theta. To get this angle, you would go tan neg 1 of 1 over neg 3 and adjust it for that quadrant. Or you could just go 1 over 3. Okay. hang on, let me get this right now, 1 over 3, and then adjust it for the quadrant. So get this would be in the first quadrant, and then you'd go pi minus that angle. Okay, because you're in that second quadrant there. Or you could say the cos of the angle is -3 over root 10, and the sine of the angle is 1 over root 10. All right, and do it, trace this angle down using that sort of approach. All right, here's some for you coming up, and I've done this one on the Casio. So this is just saying again, run mode, hit options in there, options, and then come to this window and choose complex by hitting F2 down the bottom there, F3 sorry, and then you can have absolute value, the argument, and so on for your complex number. So you can put in arg in brackets 1 plus I, and if your run mode is set up as math, so here if you go shift menu in the Casio, you want math format. Generally it stays in there in that's for this course. Math format for run mode is the most convenient. Then you'd get it in pies, or pi on 4 there, okay, or you can convert that to decimal form. So you have got the calculator as a backup there. All right, so here's the final exercises, 2D4, and see what you make of that. A little link here with sum and product of roots back in quadratic equations. So that's an interesting relationship as well. A little calculator work there too. Okay, let's have a look at the answers. 2D4, question 1, 2 and part of 3 there. Okay, we'll just come down a little bit more, we might be able to get on. Rest of 3. And 4, can we get it? I think we can. Yep, we've got that on there. All right. So our final equations, final equation there, remember the K to generalise it. Okay, how are you going? Need to study this one. We're building up fairly rapidly now. So I hope you've enjoyed that. There's further presentations come with complex numbers, so look forward to that. But for now, cheers from me.